if we make it more user-friendly, if we make it more derivative-friendly, you would want to take and rewrite it like that. And then when we take the derivative, remind you what happens. The 2 comes down in front. That's why it became a 2/3. The power goes down by 1, so that's x to the first. The -3 comes down in front. That becomes a +9. The power goes down by 1. And then if I know I have an x value to plug into these, I normally do not attempt any type of simplification because the number will allow me to do that. What's great about 1 is 1 to any power is just 1. So we get 9 plus 2/3. 9 is 27/3 plus 2 more brings us to 29/3. Okay. So today we are talking about the derivatives of our trig functions.
What are you doing? You could not do that. She's trying to touch me. Are these mine?
Yeah, let me give those to her.
So funny, so funny. I just got water. No, it'll be okay. I just like using my black.
Oh.
I don't have my friends in the garden either.
You're welcome. I love it. You're welcome. Okay.
All the way through.
She couldn't write it.
So, first 2 facts to know: that the derivative of the sine is the cosine. The derivative of a cosine is a sine. So put this on the front of your on your note card, your flashcard, and cosine on the back. The derivative of the cosine of x in terms of x is negative sine of x. So you have to know those first 2 facts by heart. You have to memorize them. This is the front, this is the back. This is the front, this is the back. So the derivative of a sine is a cosine. The derivative of a cosine is negative sine. I can't, there's no way for me to help you memorize those facts. You just got to do it, okay? You just got to do it. So please note that the derivative of a sine is a cosine. The derivative of a cosine is a negative sine. Now, one little trick that might help: all of our cofunction derivatives, whether it's cosine, whether it's cosecant, whether it's cotangent, they are all going to have a negative in front of theirs. Those ones always have a negative. The cofunctions are always going to be a negative. So let's, derivative of a sine is a cosine. The derivative of a cosine is negative sine. Now, they name these formula 311 and 312, but it's just a fact. Just know. You don't really need the 311 and 312.
I wrote them down because I wanted.
You do that. Okay. Now, if you want to find the derivative of this, the first thing we need to do, and I like what you said, I want to make it derivative friendly. And so we want to think about this as x squared times the sine of x. The reason we want to think about that is we have to use the product rule. Now, yes, we have to use the product rule, but every time we go to take a derivative of a certain thing, if it's a power function, we have to use a power rule. If it's a sine, we have to know what the derivative of a sine is. So let's go ahead and do it using our product rule. So the product rule is the first times the derivative of the second plus the second times the derivative of the first. Okay, that's it. So by knowing what the derivative of a sine is, when we get to the point where we say, oh, I have to take a derivative of a sine, I just know it's cosine. Okay, now I would assume if you had to manipulate this or do something to this function, you would want to write it as x squared cosine of x plus 2x sine of x. Put that 2x in front to make it seem, not yet, okay. I saw them coming down there. I would sometimes put that 2x in front, okay. So that's it. So we're just going to be combining all the rules of our original flashcards with the new rules. It's just when we come to a trig function, it's just a fact you're going to have to memorize, okay? Next, 4. That's why you should have 6 flashcards. The derivative of a tangent is a secant squared. The derivative of a cotangent is negative. Remember I told you that cofunctions are always negative? Negative cosecant squared. The derivative of a secant is secant tangent. The derivative of a cosecant is negative cosecant cotangent. So we have 4 more facts. Front of your card, back of your card, front of your card, back of your card, and so on. Yep. Hey, if I can memorize it, you can memorize it. Yes, okay, but you've been doing math since kindergarten.
Not this math since kindergarten.
You know what math I was doing in kindergarten?
1 plus 1.
1 plus 1. Yeah. That's about it. They told me how I started throwing letters in there.
I know.
The letters were okay. This kind of lettering, no.
When you throw in like words, like what?
Little words? What am I doing with that? This is hot. I think you try to make our brains hurt. Like, shit.
1, 4 is what was the x? No, these are so much harder than
I'm gonna be looking at it like, how do I do this?
I'm gonna need to use these on the test, Miss Fox. She didn't say no.
She didn't say anything.
I did not.
Oh, she's implying something.
These are facts that you're going to have memorized. Please make sure you know.
No.
So look at our cofunctions. Look, those are the ones with the negative. So cosine had a negative on it. Cotangent has a negative on it. Cosecant has a negative on it. Okay? Every time you write it down, it's going to stick in your brain a little bit more. So it's not a bad idea to write it down in both places. I always learned facts better if I wrote them down 5 times. So if I was going to study for a test, I would write these facts down 5 times. So writing them down twice is not going to hurt your brain. Go for it. Do it. Do it. Do it. You're good.
At least I'm done. Am I all done with my pen for the day?
Huh?
I'm not going to remember that.
Like whenever I start writing, I just think
You don't think it as you
it's
write?
just muscle memory at that
It
point.
depends upon the thing. For me, the action of writing actually helps stick it in my brain. So there's really three types of learning. There's, yeah, that helps me. Writing or typing is a kinesthetic, I think it's called. It's an action, and that will help you memorize things. Seeing or hearing. So if you're a person that's an auditory person, you would want to say it 5 times out loud. So that's why I've sometimes had you say those facts out loud. And then for a visual person, the act of writing it while you watch it. So if you can combine any of those, hearing, writing. So if you say it while you write it and you watch it, that's 3 of them all at once.
When you use
Exactly. When someone just can't remember math. I can remember everything so well. Like if you ask me to like name stuff about sports science, I'm like, got it.
couldn't be that.
So let's take a look at our, you guys, I am recording this. Let's look at example 2. It says to differentiate the fraction secant of x over 1 plus tangent of x. So I'm going to patent what was said earlier. We have to make it derivative friendly. So we're going to need to put this bottom part in parentheses. So that would be my hint to you, so that we remember we have to use, I can never spell the word quotient. Is that how you spell it?
Yes.
Okay. So yeah. So you have to use the quotient rule on this derivative. Okay. So if it says to find the values of x where the function has a horizontal tangent, we are really looking at where does the first derivative equal 0. Well, you have to equate that thing in your brain. Horizontal tangent, derivative equals 0. We'll probably even throw that on a flashcard if we haven't put that on one already. So if we go to take the derivative, we write down the bottom. We multiply that by the derivative of the secant. We just learned a little bit ago that the derivative of a secant is secant tangent. Minus the top times the derivative of the bottom. Well, the bottom is a sum, so we're going to just take each derivative individually. The derivative of 1 is 0. The derivative of a tangent is a secant squared. Now, a secant squared, for future reference, please. A secant squared written like that technically is that. Okay, so let me look at the notation. A secant squared technically is that. Mathematicians, if they can find a way to be lazy about their writing and their notation, they're going to be. So they just put it there as a little shortcut so they didn't have to write the parentheses, but that is what that means. The reason they don't put it just like a secant of x with the 2 there, because is the 2 on the whole secant or is it just on the x? So then it differentiates between those two things. Okay, now we're not done with this. We have to take it over the bottom squared. So that quantity just put in parentheses. Now that's it, but we're not done. It says, for what values will the tangent lines be horizontal? So horizontal lines have a slope of 0. So the first derivative depicts a slope of a tangent. So where does that thing equal to 0? Well, what's great is something like that can only equal 0 if a fraction only equals 0 if the top is 0. So we don't care about the bottom. We are just going to focus on where does the top equal 0. And I'm going to multiply it out a little bit. So I'm just multiplying it out. So we have secant of x tangent of x plus secant tangent squared minus secant cubed equals 0. Now, what does each one of those things contain a secant. So algebraically, we're going to remove a secant. Okay. Now, what's left, I'm going to write it in a slightly nicer order so it will be a little more factor friendly. Okay. So I'm going to put, when I took out the secant from this term, I'm left with the tangent squared. I'm just checking to make sure I did it right.
Would it be wrong if we write like tangent x squared?
Yes. Because I don't know if you mean without the parentheses, it almost is implying that your x is squared and not your tangent value. So be careful with that. I'm just making sure we did it right. Where I did it right. Bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Yeah, we did it right. Okay. I was hoping it's going to be factorable. It's not looking promising. Oh, it is. Oh, gosh darn it. So, Trig's come back to haunt us. I'm so sorry. Do you guys remember the fact that 1 plus a tangent squared is equal to a secant squared? Do you guys remember that fact? So everything else is a tangent but this. So I'm going to replace that with a 1 plus a tangent squared. So your trig identities, remember 1 plus tangent squared is secant squared is a trig identity. Trig identities are sometimes helpful. So we would get minus 1 and minus the tangent squared. So to save space, the tangent squares are going to cancel. So we just get the tangent of x plus 1. So it did simplify that quite a bit. Okay. So now it's just where is the secant equal to 0? Where is the tangent x plus 1 equal to 0? Well, the secant, yeah. It would be minus 1. Oh, so that one. Oh, you're so smart. Like what? This one should be negative. I'm so sorry. Thank you for that catch. So there to be negative. So let's make that tangent of x equals 1. Okay. Now, the secant is the reciprocal of the cosine. And if you looked at the graph of a secant, like if you pulled up Desmos and you put secant in, the secant graph looks something like that. Is it ever equal to 0? Okay, let me show you again. Secant graph looks something like that. Does it ever touch 0? No. So that one's out. There's nothing there. Boop, can't do that. But the tangent does equal positive 1 where the sine and the cosine match. Well, the sine and the cosine match at 45 degrees in our first quadrant and in our third quadrant, pi over 4. So the answer is pi over 4. And I'm going to write it a little differently. Pi over 4, and then the one in the third quadrant is 5 pi over 4. Now, it's any loop around that lands there. You might recall back in trig, it was called coterminal angles. They did not specify, so it was every one of those, every time I land at pi over 4. So to mark that, you just put this little 2 pi n, where n is an integer. So it's at pi over 4, and then another loop around, and then another loop around, and then all the coterminals with 5 pi over 4. And that's how you write that more algebraically. You put that plus 2 pi over n. N is, that's z. Capital Z means integers. So 1, -1, 2, -2, 3, -3. Yeah. Yeah, I'm sorry. This says that n is an element of the integers. That's that again, mathematicians love their shortcuts. So that just says n is an element of the integers. So any integer would go here. So that would be 1 2 pi's, 2 2 pi's, 3 2 pi's, 4 2 pi's, or all the negatives. That's just going to flip us around the unit circle. So hard one, lots of stuff to think about in that problem. Okay, lots of stuff to think about in that problem.
Isn't that the same as pi over 4 plus pi after, where n is equal to an integer?
Yeah, if you combine the two. If you combine the two, you could do that. Yeah. Okay, let's take a look at this one. It says find the derivative. There's no way to make that user-friendly, derivative-friendly. So we're going to just use that as a quotient. So when we use that as a quotient, we have to, bottom times derivative of the top minus top times derivative of the bottom, all over the bottom squared. Okay, so bottom times the derivative of the top. What did we learn that the derivative of a cosine was equal to? Negative sine. Minus the top times the derivative of the bottom, all over the bottom squared. Now, I do not require that you do anything past that, unless it asks us to find where is it a horizontal tangent, where is it blank, where is the tangent equal to blank. If we had to do something more algebraically with it, we would deal with that. But for now, just do the derivative and walk away. Okay? That's it. So that's any questions on how we got that? Okay. Now, you recall that we had done in the last section applications of derivatives. Many times particles, sound waves, travel in sine or cosine waves. So in motion equations, it is very, very true in real life applications that you may end up with a sine or a cosine in there. It's just the nature of the movement of waves. So because of that, it is common to have an equation containing a sine or cosine when it comes to motion. So it says a particle moves along a coordinate axis in such a way that at its position at time t is given by the s sub t equation there. We are only carrying about one cycle around the unit circle, so they did specify between 0 and 2 pi, which makes our life a little easier. We don't need to do that plus 2n pi. It's just somewhere between 0 and 2 pi. At what time is the particle at rest? So remember, you have to know that that's a fancy way of saying that our velocity equals 0. So if we have our position function and we want the velocity function so that we can see where it's equal to 0. Remember, the velocity function is just the first derivative. So just take the position function and take the first derivative. The derivative of a sine earlier we learned was a cosine. So that's 2. The constant just acts like a constant, just hangs out for the ride. So that's 2 cosine of t. And what is the derivative of a t? 1. So that's a minus 1. So we're looking for where does that equal 0? Okay, so we have a little math to do. So we know that the cosine of t would equal 1/2. We would move the 1 over, it'd become positive, divide off the 2. Hopefully that doesn't confuse you, that you know that what I just did. Now, here's our knowledge of the unit circle. We are only looking for one flip around and where the cosine is positive. So if we look, the cosine is positive here and here. So that's where we're going to search for our answers. The cosine is our x value at 60 pi over 3. The point is 1/2 square root of 3 over 2. And down here, which would be 5 pi over 3. would be also 1/2, but negative square root of 3 over 2. And all you care about, remember, is for a cosine, the x values. So we are looking for an answer at time pi over 3 and at time 5 pi over 3. Now, how could time have an answer that has a pi in it? Well, that just means use your 3.14 unless it tells you otherwise. So 3.14 divided by 3. So at time approximately 1.05 seconds, at that place it stops. 5 times 3.14 divided by 3, and it stops again around 5.23 seconds. Now, it didn't specify how many decimal places. So since pi is usually rounded to 2 decimal places, 3.14, feel free to round it, your answer to 2 decimal places. So you'll notice we do have to still remember some of our trig functions. Hence why at the beginning of the year, I made you look at those things again. Any questions about that particular question? Okay. So now let's talk about how we find equation of tangent lines. It's the same thing, same 3 steps for these. First thing you do is find the derivative. Second thing you do is find the slope of the tangent using that derivative. Third thing you do is y minus y1 equals m times x minus x1. That doesn't go away even if it's a trig function, whether it's any of the rules we're going to learn about derivatives. Doesn't matter. That's the 3 steps you want to take. So the first thing we're going to do is find the derivative of a cotangent. So if you were to look at your cards, I always remember tangent first. I always remember sine, cosine, and tangent, maybe even secant. I remember the unco ones usually help me with the others. The derivative of tangent was secant squared. The derivative of a cotangent, just throw a co word in front of it. It's cosecant squared, but what does the cos always have in front? A negative. So that's negative cosecant squared. So it's just a rule you got to know. You just got to memorize them. I will tell you that sine, cosine, and tangent are the ones used most often. Every so often secant, but anyway, that is our derivative. And they want to know what, remember, that was our first step. Second step, to find the slope of the tangent, we just have to plug it in. Okay. Does anybody recall what reciprocal is the cosecant? Yes, it's the sine. The flip of the cosecant is the sine. So at pi over 4, we know the sine of pi over 4 is square root of 2 over 2. So the cosecant of pi over 4 is the flip of that, and if you simplify it and flip it, you always get just the plain old square root. It's really nice. Okay. So this is really just going to be the negative square root of 2 squared. Now let's think about why. This notation means you square the value at that point. So the value at cosecant of pi over 4 is square root of 2. We're just going to square it, but don't forget there's a negative in front. And so the answer is negative 2 is our slope. Now, the third step is to use this, that point slope formula. We got to have a point. They gave us an x. How do we find the y that goes with it? You just plug it in. You just put it back into the top equation. So if I plug in pi over 4, the tangent at pi over 4 is square root of 2 over 2 over square root of 2 over 2. It's 1. So if I flip that, what am I going to get? 1. So the point at pi over 4, the x value is pi over 4, the y value is 1. And so we're going to use a slope of negative 2 that we found earlier. We're going to use the point pi over 4, 1. Now, I don't care that you simplify it. I care that we're going to plop the information in, walk away, just like our derivatives. If we don't need to reduce it, Don't waste your time. I know you know how to find the equation of a line. I don't question your algebra, even if I should at times. But what I do, just plop it in, okay? So it's going to be y minus 1 equals negative 2 times x minus pi over 4, pi over 4. Now, if you want to simplify it, go for it. You would distribute the negative 2 and add 1 to both sides. I don't care. That doesn't do anything spectacular for me. I don't care. That's the equation of the line. If I needed to do something with it, I would. They didn't ask me to do anything more. I'm done. Does that make sense how I did that? Okay. These facts, please just write them in your notes. If we come across some examples that use them, do you remember how we were doing limits? And when we were doing limits, if we got 0 over 0, I would tell you to manipulate the algebra. Well, if you plug in 0 for both of these, you do get 0 over 0, which is undefined. And we can fix the problem. But to actually fix the algebra in this is so difficult. So someone else did it for us. That's all you got to know. If you plug in 0 over 0 here, you would get, or I'm sorry, if you plugged in 0, you get 0 over 0, undefined. Fix the algebra. Oh, they fixed it for you. The answer is always 1. If you see this, the answer is always 0. So that's just 2 facts that we're going to add to our arsenal. We may put them on a card at one point, but for now, just write them in your notes. I'm just going to show you something real quick of how to find these. Again, this is not something that's super important, but the formula says that the limit as x approaches 0 of the sine of theta, well, let's use the same variable everywhere, Mrs. Hahn. As theta approaches 0 of sine of theta over theta is always equal to 1. So what you do here basically is you manipulate it so that you can find how it relates to 1. And here's the trick. See how there's a 7 right here? But there's not a 7 down here. You're going to multiply both top and bottom. We're just gonna trick it. We're going to multiply the top and the bottom times 7. Then we're just going to rearrange the algebra a little bit. We're going to leave the 7 here because we can't do anything about it. And here we're going to pull out the 4, but leave the 7 with the x. Now, once these match, that always reduces down to 1. And it's the math is so hard to get there. You just got to take that on faith. that becomes 1. So that becomes 1. So what is 7/4 times 1? 7/4. It's just a weird sort of kind of manipulation and rule. We're not going to really do many of these at all ever, but I did want you to at least see it, okay? And then you got some homework. So remember, tomorrow in class, please work on the 3-4 and 3-5 homeworks. Next week on Monday, remember that derivative thing that had the 200 questions that we had started and we only had pulled out some questions to do? Monday, we're going to do some more. Tuesday, we might do a little bit more. Before we do the chain rule, which is even a layer upon this stuff, you have to know the other stuff, okay? There's so many layers. It is an ogre. It's like an onion. Yeah.